Hi everyone, in the video we'll be talking about how coupling works in HNMR. In the case of proton NMR, the NMR spectra can often get complicated quickly due to coupling with neighboring protons. The multiplicity of a multiplet signal, whether it is a triplet or doublet and so on, is given by the formula n+1, where n is equal to the number of equivalent protons attached to neighboring atoms. Let us take a look at proton NMR, which is ethyl acetate. We will first identify the protons that have different chemical environments. For ethyl acetate, there are 3 different environments, and we label them A, B, C as seen here. For example, for Hb, the number of neighboring protons is 0. Hence, according to the n+1 rule, this results in a singlet in the proton NMR spectrum for Hb. For Ha and Hc, the number of neighboring protons is 2 and 3 respectively. Therefore, according to the same n+1 rule, this will result in a triplet and quartet respectively.
The chemical shift a proton experiences is largely dependent on the local magnetic field that the nucleus experiences. In general, electronegative atoms or electron withdrawing groups will reduce the electron density around adjacent protons. This dishews the adjacent proton, causing the proton to experience a greater effective magnetic field. This means there's a greater difference in energy between alpha and beta spin states. Bigger energy difference corresponds to a higher frequency as compared to protons further away from the electronegative oxygen atom, as they experience less electron withdrawing effects. Higher frequency signal will thus lead to a higher chemical shift. The signal will thus move downfield towards the left of the spectrum. However, the opposite holds true for proton A. Proton A is attached to an electron donating alkyl group, which increases the shielding effect around itself. Hence, proton A experiences a smaller effective magnetic field, hence leading to a smaller difference between the spin states. This in turn means a lower chemical shift, and the signal for proton A will shift outfield towards the right in the spectrum.
But that's not it. More complex splitting patterns can be observed. Taking this NMR spectrum as an example, the proton we label as Ha is adjacent to non-equivalent Hb on one side and Hc on the other. As seen in the diagram, the 3 protons present are in different environments, as Ha is cis to the cyanide group, while Hb is trans to the cyanide group, where the difference in proximity to the cyanide group affects their chemical environment. Originally, we might expect Hc to display a triplet signal due to the presence of 2 protons attached to the adjacent carbon. However, Hc actually couples to Ha and couples to Hb differently. Thus, there will be 2 different coupling constants, one between proton A and proton C, and the other between proton B and proton C. Therefore, instead of a triplet, a doublet will be formed due to proton A, and another doublet due to proton B, leading to the formation of a doublet of doublets. Thank you for your time, and we hope you learned something from the video.